In the previous part of thermodynamics, we talk about the quantity of heat, Q, as a function of the mass heat capacity or the molar heat capacity, and we define dQ equal m, the mass, times Cs, the specific heat capacity, dt, or dQ equal n, the number of moles, times C, which is the molar heat capacity, dt. So to find dQ, we have to solve the integration, and we have two cases. C is temperature dependent or C is temperature independent. We pass to example 5.1. How much heat is absorbed by a copper with mass 3.10 grams and the temperature increase from -8 degrees to 37. First of all, this is a physical transformation. This is an important question at the beginning of any exercise. Is the transformation physical or chemical? We said that the concepts are very close, but some calculations are different. So this is a physical. Since we have copper initially and copper at the final state, but the difference is in the temperature. Initial temperature equal -8 and final temperature equal 37. To increase the temperature of any substance, we have to give energy or to give heat to the substance. For this reason, the heat is absorbed. And since the heat is absorbed, so the value of Q should be positive. Initially, the temperature -8, the temperature final 37, and the mass equals 3.10 grams. So for physical transformation, at condition that we don't have a change of state, I have copper solid at -8 that is transformed to copper solid at 37 degrees. So the copper did not change its state. When we have a physical transformation with no change of state, we apply directly the relation dQ equal mCs dt. Why I use Q equal mCs dt? Since in the exercise, the specific heat capacity given is Cs, which is per gram. So dQ equal mCs dt implies integration of dQ from state 1, from initial state 1 to final state 2 equal integration from 1 to 2 mCs dt. And since the mass is constant and Cs is temperature independent, so we obtain Q equal mCs delta T. And delta T equal T final minus T initial equal 37 minus -8, so delta T equal 45 degree. Q equal mc delta T, m equals 3.10 times Cs, which is given 0.385 joule per gram per degree, times delta T 45, so Q equal 53.7 kilojoule. What is the meaning of this value? In other words, if you give to a piece of copper where its mass equals 3.10 grams, you give, for example, 53.7 joule as heat, as energy, you will increase its temperature from initially -8 to T final equal 37. What is the definition of the energy flow? When energy flows into a system, it must all come from the surrounding. In the next slides, we will talk about the first principle of thermodynamics, and we will see that the total energy of the universe is constant. So the system can gain energy from the surrounding, or the surrounding gains energy from the system. So we will have exchange of energy between system and surrounding. When the energy flows into a system, suppose the system absorbs this energy, so delta E of the system is positive. This energy absorbed is delta E, should be positive. In this case, the surrounding lose energy, so delta E is negative. Between system and surrounding, we have energy flow. If the surrounding lose energy, so delta E surrounding is negative, and this energy will be absorbed by the system, delta E of the system is positive. Pay attention that the energy absorbed by the system is equal to the energy lost by the surrounding, but the transformation in the system is different from that happening in the surrounding. We have a transformation in the surrounding that release energy to the system, and the system will absorb this energy to make a transformation, but the transformation in the system is different from that in the surrounding. Work. What is the definition of the work? Chemical reaction can do several different types of work. And in the next slides, I will talk about the work of chemical reaction. The chemical reaction, for example, in our car, we burn fuel. So we did a chemical reaction. This chemical reaction is transformed, will release energy, and this energy will be transformed to a work, okay? Will be transformed to a work, and the car will go on. So I will talk about the work only in physical transformation. In the physical transformation, we will also consider the work of gas. And the gas is characterized by a pressure and volume. So we will talk about the pressure volume work. So the work in the physical transformation is related to the pressure and is related to the volume. The definition of the work is a force acting through a distance. The pressure volume work occurs when the force is caused by a volume change against an external pressure. I will explain this in detail. So I give now only the definitions of the work, but I will explain later the formula for the work of a physical transformation. So the work is equal to the force times distance, and the work is equal F times D. And we know that the pressure is force over area, so F equal PA. Substitute PA in the expression of the work equal FD. So W equal the pressure times the area times the distance. And distance is, for example, in this example, I have expansion of gas or compression of gas. So the variation of the volume is the difference of height between the initial state and the final state. So the initial state is the state before expansion, and the final state is the state after expansion. So the change of the volume before expansion and after expansion can be related to the difference of height. So W equal PA times delta H, and we know that area times delta H is the difference of volume. So the work is P times delta P. This is the work only for a gas. I consider in the physical transformation the work of a gas, or what we call the pressure volume work. So as a conclusion, it's not necessary to do all this proof. You can use directly the relation. As a conclusion, the work is directly related to the pressure, and the work is directly related to the variation of the volume. So now we have to correct this formula. Is this formula in this form true, or we have to do some modification? Previously, we wrote W equal P delta V. Suppose we have expansion. Suppose we have expansion of a gas. So the volume final is greater than the volume initial, or in other words, the volume of the gas after expansion is greater than the volume of the gas before expansion. So delta V is positive, and the pressure is positive. So if we write the expression W equal P delta V, W will be a positive value times a positive value. In this case, W will be positive. And we are talking about expansion. In the expansion, the work is done by the system, by the gas inside the cylinder on the surrounding. Okay, so the work should be negative. By the definition of work, the work is negative since this is a form of energy that is given to the outside, to the surrounding. So the work is negative. And if we write W equal P delta V by this way, the work will be positive. So we have to correct the sign of this formula. The sign of this formula, so the formula will become dW, the variation of the work, is equal minus, we put sign minus P times the variation of the volume. So as a conclusion, what is the work? We consider the work done by the system on the surrounding, and the variation of the work directly can be used dW equal minus P dV. This is the formula of the work that can be used without a proof. When a gas is compressed, this is the opposite of the expansion. Delta V is negative and the W should be positive since the work is done on the system, indicating that energy enters the system. So now we know that dV is the variation of the volume between the initial state and the final state. So what is P? P is the pressure of the gas internal or the pressure of the gas external. So is the pressure of the gas internal or is the P external applied to the gas? When we compress, we give the pressure to the cylinder, so we give P external, but this P external is equal to the P internal. So in many cases, the external pressure is the same as the internal pressure of the system. So P external is just represented as P. So the formula dW should be equal minus P external. In some books, you see dW equal minus P external dV. In other books, they represent the formula as dW equal minus P dV. Why? Because in most cases, the P external applied to the gas is equal to the P internal of the gas. For this reason, we prefer to use only P. As a conclusion of these two slides, what is the work in a physical transformation? The work in physical transformation is represented by dW equal minus PdV, and to solve or to find the work, we have to solve the integration of dW and dV. What is the unit of the work? The work is a pressure times volume. So the work obtained will be in atmosphere times liter. But in the international system, the work should be in joule. We use the conversion of the units to joule. 1 atmosphere liter is equal 101.3 joule. All the conversions will be given in the exercise. We pass to the calculation of the work dW equal minus P external dV, or dW equal minus PdV. So we solve the integral of dW from initial state 1 to the final state 2 equal minus integral from 1 to 2 P dV. So integral from 1 to 2 dW is W. Now we have two cases. Consider the transformation from system 1 to system 2. This is the initial state, and this is the final state. In the integration, we have P, and we have a pressure and volume. We have two cases. The pressure is constant, so it's independent of the volume, so P can be put outside the integral, or the pressure depends on the volume, so we have to substitute the pressure by its function to the volume. Then we solve the integral. Instead of P, we put function of volume dV, and we solve the integration FV dV, the function of the volume times dV. The first case, the pressure during the transformation is maintained constant. So W, integral from 1 to 2 dW, W equal minus integral from 1 to 2 P dV. P is outside the integral. So we have integral from 1 to 2 dV, and the formula W equal minus P V final minus P initial minus V initial. The second case is when the pressure depends on the volume, and this is the case when we have ideal gas in system 1 and ideal gas in system 2. The ideal gas, by definition, is characterized by some properties. The pressure has a pressure, has a volume, has a certain number of moles at known temperature. For ideal gas, these properties, the pressure of the gas, the volume of the gas, the number of mole of this gas, and the temperature applied to this gas, or the temperature of the gas, are related according to an equation known as ideal gas equation, PV equal nRT. This is the relation that relate the pressure, the volume, the number of moles, and the temperature of an ideal gas. R is a constant given, which is equal 0.082 liter atmosphere mole minus 1 Kelvin minus 1, or in other unit R is given 8.314 joule mole minus 1 Kelvin minus 1. So suppose In this transformation from system 1 to system 2, we have ideal gas. So we cannot put P outside the integral since P in this case is variable. It depends on the volume. And since the volume is variable, so P is a function, is variable, is a function of the volume. So what to do? We have to substitute P as a function of the volume. PV equal nRT. So P equal nRT divided by V. Therefore, W equal minus integral from 1 to 2 P dV. So equal minus from 1 to 2, instead of P, we put its function to the volume nRT divided by V dV. N is constant. The number of moles of gas is constant. R is the ideal gas constant. Temperature, since we talk about two variables, pressure and volume, so the two others should be constant. If we have two variables in the properties of the gas, the two others are maintained constant. So N is constant, R constant, temperature is constant. So we obtain minus nRT integral from 1 to 2, 1 over V dV. 1 over V dV, the solution of the integration is ln V. So W equal minus nRT ln V2 divided by V1. These two relations can be applied also directly without a proof. For a transformation from system 1 to system 2, where the pressure of this transformation is maintained constant, so W equal minus P delta V directly. In the transformation where the pressure is related to the volume, this is, for example, the example of the ideal gas. So to solve the integration, we have to substitute P by its function of V. So for ideal gas, PP equal nRT and P equal nRT divided by V. So the work is equal minus nRT ln V final divided by V initial. Example 5.2. In a balloon inflated from 0.1 liter, this is V initial, to 1.85, this is V final, against an external pressure P equal 1 atmosphere. Watch how much work is done. So we have a balloon where the volume of the gas initially is 0.1. The balloon is inflated to V final equal 1.85 liter, and the P external on the balloon is 1 atmosphere. So what is the work done? We apply the relation V initial equals 0.1, V final equal 1.85, P external equal 1. The pressure is in this exercise is constant. We don't have any indication that the external pressure is variable against an external pressure 1 atmosphere. So the pressure is given constant in this exercise. So W equal minus P delta V directly. And delta V equal V final minus V initial 1.85 minus 0.1. So equal 1.75. So W equal minus P delta V equal minus P 1 atmosphere times 1.75. So it's equal to minus 1.75 liter atmosphere. In the international system, W should be in joules. So we apply the conversion. 1 atmosphere equal 101.3 joule, and then the value is equal minus 177 joule. Pay attention in this exercise before starting the calculation. This is an expansion. The balloon initially 0.1, final 1.85. So the work is done by the system, which is the balloon, on the surrounding. So the work should be negative before starting the exercise. The work done by the system on the surrounding, the work negative. The work done by the surrounding on the system, the work is positive. So our value is correct since the sign is minus, is negative.